Welcome to Chapter 12.2. In this section, we study techniques for evaluating limits algebraically. So far, we have learned how to evaluate limits graphically and by using the table feature of the calculator. In this section, we will study four main algebraic techniques for evaluating limits. They are direct substitution, dividing out, rationalization, and simplifying complex fractions. Let's start off with direct substitution. Whenever you are evaluating a limit algebraically, always begin by trying direct substitution. And when I say always, I mean every single time. Always begin by trying direct substitution. To complete direct substitution, simply substitute in the value that x is approaching into the function. If the result yields a real number, that is your solution. Simple as that. Evaluate the following limit algebraically. We have the limit as x approaches negative 1 of x squared plus 2x plus 2. All we have to do is substitute in negative 1 for x. All right, that is our direct substitution. This gives us negative 1 squared plus 2 times negative 1 plus 2. This gives us 1. And because our answer is a real number, that is our solution. We end up with 1. It's a real number. That is the answer to our limit. The limit as x approaches negative 1 of x squared plus 2x plus 2 equals 1. The limit as x approaches 2 of x squared plus 2x plus 1. Well, here we're evaluating the limit as x approaches 2. This simply means that we can substitute in 2 for x. 2 squared plus 2 times 2 plus 2. This gives us 10. And because 10 is a real number, that is our solution. Let's see if it makes sense graphically. Here I have the graph of the function y equals x squared plus 2x plus 2. Remember, limits tell us what happens to the y values as x approaches some given number. And in this first limit, we were looking at what happens to the y values as x approaches negative 1. Well, here I have x equals negative 1, and as I'm traveling along my curve, as my x values get closer and closer to negative 1 from either side, what are the y values getting closer and closer to? They are getting closer and closer to 1. Similarly, our second limit, we evaluated the limit as x approached 2. Here I have x equals 2. As I'm traveling along my curve and my x values are getting closer and closer to 2, what are the y values getting closer and closer to? Well, the y values are getting closer and closer to 10. Therefore, our answer of 10 makes sense. Let's look at a couple others. The limit as x approaches negative 3 of x squared minus 1 divided by 2x plus 1. Again, anytime you are evaluating a limit algebraically, begin with direct substitution. Because we are evaluating the limit as x approaches negative 3, we are going to plug in negative 3 for x. This gives us negative 3 squared minus 1 divided by 2 times negative 3 plus 1. Simplifying, we end up with negative 8 fifths. Again, we get a real number. That is our solution. The limit as x approaches 1 of x squared minus 1 divided by 2x plus 1. Here, we are going to substitute in 1 for x. This gives us 1 squared minus 1 divided by 2 times 1 plus 1. Well, 1 squared minus 1, that gives me 0 in the numerator, divided by 3. Well, 0 divided by any non-zero real number, that is simply equal to 0. 0 is a real number. That's our answer. And we can verify our solutions graphically. Notice our first limit was the limit as x approached negative 3. Right? As my x values get closer and closer to negative 3, the y values are approaching negative 8 fifths. Okay, that looks like a reasonable answer. And similarly, we had the limit as x approaches 1. Well, here I have x equaling 1. What are the y values getting closer and closer to as the x values get closer and closer to 1? They are getting closer and closer to 0. Again, verifying our answer with the graph. Let's look at a couple more. Evaluate the following limit algebraically. We have the limit as x approaches 0 of cosine x plus 1. Well, again, even though we're dealing with a trig function here, all we have to do is our direct substitution. We plug in 0 for x. That gives us the cosine of 0 plus 1. And the cosine of 0, well, think back to the trigonometry that we've covered throughout the year so far, and your unit circle. the cosine of 0 is 1. Therefore, we have 1 plus 1, which is equal to 2. The limit as x approaches pi over 3 of cosine x plus 1. Again, we try our direct substitution. We plug in pi over 3 for x. This gives us the cosine of pi over 3 plus 1. The cosine of pi over 3, well, that's 1 half. 1 half plus 1, that's 1 over 2 plus 2 over 2, gives us 3 divided by 2. There is our direct substitution. Again, if we get out a real number, that is our answer. Graphically, we can verify these answers. Here I have the graph of y equals cosine x plus 1. Notice that as my x values get closer and closer to 0, here's x equals 0. As my x values get closer and closer to 0, the y values get closer and closer to 2. Similarly, as the x values get closer and closer to pi over 3, that's a third of pi, the y values get closer and closer to 3 halves, or 1.5. Let's look at one more. Evaluate the following limit algebraically. The limit as x approaches negative 3 of the square root of 523. Well, in this case, the square root of 523, that is just a constant. Notice that we can consider this a direct substitution. We are plugging in negative 3 for x, but because there's nowhere to plug in for an x, that means every single value that we get out, no matter what we plug in, is going to be the square root of 523. The limit as x approaches negative 3 of root 523 equals root 523. The limit as x approaches 5 of root 523, well, again, there's no x to substitute in for. Therefore, no matter where we are evaluating the limit, the output is always going to be root 523. And you might recall, the limit of any constant is equal to that constant, right? Root 523, that's a constant. That is a number. And graphically, if we were to graph the equation y equals root 523, well, that's just a constant function, which gives us a horizontal line. Notice that no matter where we evaluate the limit along this horizontal line, we are always going to get the square root of 523. As our x values get closer and closer to negative 3, the y values are always root 523. As the x values get closer and closer to 5, the y values are always root 523. So again, the limit of any constant is equal to that constant. So there you have the first technique for evaluating limits algebraically. Direct substitution. Simply plug in the value that x is approaching for x and simplify. If you get out a real number, that is your answer.